So we can go ahead with the next presentation, keynote presentation by Dr. Anis Rahman from USA.
Good morning, good afternoon, good evening. Let me share the screen for my presentation. Okay. Are you able to see my screen?
Yes, we can see it.
And then, okay.
Thank you.
Thank you for the invitation, and I'm really happy to be able to share some of the work that we do here at Applied Research and Photonics Incorporated in Harrisburg, Pennsylvania. Today, I'm going to talk about nanoparticle interactions, importance and investigation by non-destructive cameraless terahertz lattice-scale imaging. So briefly, I will go through some introductory material and nanometrology and why cameraless imaging is important, how we do it, and then some examples of a quantum dot ionic polymer matrix system and layer by layer imaging and inspection. And if time permits, I will also go into a little bit of spectroscopy, terahertz spectroscopy. So the applications of nanomaterials require deeper understanding of these materials and their interactions with other materials. The most critical knowledge gaps and challenges are in the following areas: measurement and standards for manufacturing, characterization of nanomaterials, interactions between nanomaterials and the bulk, characterization of interfacial properties, and of course the environmental issues. So the measurement and standards for manufacturing involves so let us first set the terms here, which are measurement or metrology is the basis for all characterization. So by measurement, we mean routine analytical work. By characterization is more absorbed and elaborate, in detailed analysis. Characterization also defines the key properties of the materials. For advancing the uses in the industry, new unperturbed test methods are needed. And I will explain in a minute more of that. For larger scale manufacturing, there is a need for replacing the expensive characterization methods with rapid, robust, and industrial scale techniques. So by nanometrology, we mean the measurement of any nanoscale things, such as nanomaterials, nanoparticles, nanometer size things, event time, nano to femtosecond time, etc. As the old saying goes, if you can't measure it, you can't control it, or you cannot manage it. So the measurement is the key for any field. Now, challenge is lattice resolution imaging without electron microscope or atomic force microscope, and so on and so forth. Interactions of knowledge gaps remain in the interactions of nanomaterials with itself and others, nanomaterials at surfaces and interfaces, nanolayers, defects, delaminations, etc. And semiconductors and materials alike, packaging, via meaning the hole and the fins, etc. Now, this is an example of the degree of problem in semiconductor industry, although subsequent example, I will go into ionic polymer. But as you can see, a blank wafer cost maybe $100, $200, but when all the chips are built on it, its value jumps to $1 million or more depending on what is being built on it. So it takes a long time from a blank wafer to device fabrication process development. Once the process is developed, then of course they go into production with high yield. But this developing the process is very long time. It may take years because of so many things are involved. It's not just patterning and layering and patterning and keep on going like that. There are a lot more involved in here. So if there is some undetected problem in the form of nanometer size defects, then that kills the yield, and one wafer thrown away is $1 million wasted. So similar problem also occurs in nanotechnology area. Here particularly I am going to show you of the system that has been recently published in Macromolecules in collaboration with the Argonne National Lab and the Los Alamos National Lab. So particularly the Los Alamos National Lab manufactured this, synthesized this polymer system or ionic polymer system along with the quantum dots. So the designer system is hierarchically structured quantum dot polymer composite, where the polymer comes around the quantum dots in a cylindrical form. That is also, this is artist rendering on the upper right corner, this one. And this is the small angle X-ray scattering spectrum from which they have theorized that this is the structure that is possible. However, analysis of the multi-length scale scattering was accomplished by using theory and modeling and small angle X-ray scattering measurements. Time-dependent Ginzburg-Landau calculations verify the mesoscale cylinders arise from the topological constraints imposed by the in-plane perforations of the polymerized ionic liquid as it wraps around the hard spherical quantum dots. And this is not a single wrap, it's layer after layer after layer wrapping, as we can visualize from the artist rendering. So we have conducted Terahertz multispectral reconstructive 3D imaging, and by which it was revealed that the surface structure along the cylindrical axis undergoes dynamic rearrangement between 2D hexagonal and cubic packing. And Terahertz imaging was essential because everything else can see only the surface, not under the surface in 3 dimension without in a destructive mode. Now, as a company, we are actually a private company. We started back in 2003, and we have come a long way at a very slow pace. It took a long time for us to achieve nanometer resolution and subsequently lattice resolution imaging capabilities without camera, without CCD, by overcoming the AVI diffraction limit. So as far as imaging is concerned, this optical lens-based imaging system is defined by the AVI paradigm or AVI diffraction limit. Simply speaking, the image resolution cannot be less than half the wavelength that is being used for imaging. So if you are using, let's say, UV light, if it has some 256 or so nanometer wavelength, the smallest object one would be able to image is half of that, 128 nanometer. Electrons have a wavelength in picometers, therefore we can see atomic lattice with them. The electron microscope, some of the difficulties are that it impinges high energy and many delicate samples get destroyed. X-ray also can penetrate through many things, but X-ray is also ionizing radiation that are, detrimental to many of the delicate samples. So, so we came up with a different technique using bigger wavelength and still doing the lattice-scale imaging. And as you see in the blue, the stratagem has been worked out that deploys the Beer-Lambert's law via reflectance. So we rewrite or modify the Beer-Lambert's law in the reflectance domain, and then we use a 3D nanoscanner for digitizing an object, and then we use a special algorithm to generate the image. So we use terahertz, and T-ray is important because it can penetrate through a lot of materials, solid, liquid, etc. So it allows us to see not only on the surface, but also below the surface in the destructive mode. And there are more than one ways of generating terahertz. We specialize in dendrimer dipole excitation, which is a new mechanism, was invented by our company. And it has quite a few advantages. And unlike the legacy technology, which is the photoconductor or photoswitch that requires a femtosecond pulsed laser application of high voltage, those have been eliminated. It's also compact size, and all operations are ambient, like UCL requires low temperature. We don't need that here. Output bandwidth and power are tunable, and it's a very stable, continuous wave terahertz source. With that source, we build instruments here in ARP, and that's the one that I'm going to use here. So I have some of the pictures from the past of different events. On the left, we had a reception for the Nobel laureates, Robert F. Cardle and Harry Kroto. Sir Harry Kroto passed away recently. And they are the 1996 Nobel laureate along with David Smalley. We learned from Cardle Group because they are one of the pioneers in also terahertz generation by difference frequency method, and so we had some communication with them. And on the right, along with myself, is Dr. Donald Tamalia. He is known as the father of dendrimer, and dendrimer is the nanomaterial that we use for terahertz generation. So as again, terahertz is in the, used to known as the terahertz gap. Because there was no laboratory man-made sources for high power generation. So here is the, in a nutshell, in the bottom cartoon, as you can see, the dendrimer is a spherical molecule. Its size depends on the generation. So we have chosen a particular generation for our work. And then we dope with chromophore to create the charge centers. And in fact, charge centers distribution, they are not like inorganic lattice. They have a particular spatial distribution. And because of that distribution, when pumped with a reasonable wavelength, we get a terahertz emission from this dendrimer molecule. And this emission is broadband emission because of the quasi-stable states formed in the Fermi gap are not a single one. Because of the dipole distribution, dipole moment distribution, we have, in the Fermi level, you have more than one quasi-stable states. Therefore, the output terahertz radiation has a, a distribution. We have been able to generate up to 30 and more terahertz out of this system. Forgive me. Now, let me say just one slide about this cameraless imaging system. So on the top part, as you can see, there is an object, light reflected from that object to go through this focusing lens and falls on a focal plane array, which is a CCD or could be a CMOS sensor. And that CCD gives out an electrical signal. That electrical signal is processed by built-in ASIC in a camera, and the image is displayed and stored. So in the cameraless system, now of the CCD is the resolution of an image is set by the CCD. If I have a 48 megapixel CCD, that's all I have. I can probably reduce, but I cannot go any better resolution than that. So in the cameraless system, we have a nanoscanner on the left, as you can see. An object is digitized by the nanoscanner, and a 3D matrix of reflection intensity is created. We call it a Beer-Lambert matrix or Beer-Lambert reflection matrix. And I will show you in a second why. So that data is processed by a computer. We're using desktop computer. And via the algorithm, image is generated. So pretty much the same principle, except that we now have a nanoscanner, no focusing and no CCD. And that way we can control the pixel size from lattice resolution to all the way to much bigger, centimeter or so. And in 3 dimension, we call it a voxel. So the voxel size are also 1 cubic angstrom or less. Pros and cons of cameraless scientific imaging. This is important because the advantage is that no camera, no CCD or CMOS. A resolution chosen by user, not by CCD. A resolution from macro down to angstrom or less than an angstrom. It doesn't require any sample preparation for scientific imaging. It's independent of sample's shape and size. It can handle liquid, solid, gaseous samples on the surface and subsurface areas. It's volume image and layer by layer imaging and analysis ability, measurement of size and thickness and size distribution, equivalent functionality as AFM, SCM, and TEM without requiring the, all the thing that needs for those systems. And it's now a tabletop system, but it can be a inline system, it can be in a clean room system, so on and so forth. But the disadvantage is that you still need a scanner or a nanoscanner, and the image is not in real time. After this scanning, the image is generated, and lattice resolution image generation takes a lot of time. And also this system, unlike SEM, where elemental analysis backscattered X-ray spectroscopy is done, this system cannot do that. And it's not handheld yet. We are hoping to go to that part. Here's the system, a prototype system in our lab. We did a live demonstration at many places. One of the live demonstration picture is here. And with that, the sample mounting here is shown is the sample mounting can be done in two ways, where one sample can be mounted as vertically oriented, or in other orientation it can be horizontally mounted. For bigger sample, horizontal mounted where sample remains stationary is better. For smaller samples can be mounted straight on the scanner, and the sample will move in that situation. So here is the algorithm that we use for what we call as a gridding with inverse distance to power equation, and that generates the image. On the left, as you can see, the reproducibility of scan is very important. If we scan over and over again, we must have the same profile so that the image is the same. So same object will always give the same image. And we have proven by our interns, they have worked on this. So scanning of the same feature is very reproducible. And then we rewrite the Beer-Lambert's law, as I mentioned, in terms of the intensity, where because the reflected intensity is function of the material on this and position. If position changes and if material changes, then the reflected intensity will change. And we utilize that factor for contrast generation. So with that, let me show you the examples. One is if we here is just a hypothetical situation that if we have a cosine function, does our algorithm produce a cosine function? And yes, indeed it does in 3 dimension. It's not tomography and topography, because as you can see, if we scan in 3D and plot in 3D data, they don't show anything. It has to go through that algorithm to generate the image. Here is one of the very early work we did on chromium nanoparticles. As you can see, the particle size here is 1.7 nanometer. And you can, when you do the profile along this line, then all the particle sizes can be measured and their distribution can be estimated. Now I go to this main topic of polymerized ionic liquid quantum dot composite system. This one on the left is the this is a TEM image of the particles that shows about 10, 11 nanometer or so, which is what we about 11.29 nanometer. And when we measure with our terahertz imaging, the particle size are about the same, 9, 10, and then the chains, they are not the same particle. So there is a little bit of polydispersity, not highly monodispersed quantum dot, and these are the these are the polymers around them. We'll show more of that, but first here is the sample that we mounted on a plexiglass, and the plexiglass then was mounted on the nanoscanner and scanning was done. So with the particle size determined, then we found that some particles have some aspect ratio. Some of them are spherical. So we had a chance to then quantify those factors. And we saw that particle edge to edge is 10.49 nanometer. Here, this table shows horizontal and vertical size distribution from edge to edge, and on this table is full width at half maximum. A lot of time particles are measured that way because of the edge effect. So the edge to edge matches better with the TEM data. but also we can see that there is an aspect ratio. It's not a particularly spherical particles. Now here I am showing you a 3D image of 1 cubic micron sample. So as you can see on the left, on the 3D, one side of the 3D image, that the quantum dots are at the center and the polymer layers goes around it, and they penetrate through the length. So if I take the front surface and then slice this 1 micron at every nanometer, and that is the video on the right. So this is not an animation. On the right, you see that these are different layers. As I go from the top surface, from the top surface to the, this is a close-up of the same thing. This is my top surface, and I am going deeper and deeper and deeper. And as you can see, the particle distribution and the polymer distribution, polymer layer orientation are changing. So this is a layer by layer measurement ability. For every layer, we can measure the particle size, the polymer orientation, polymer lattice spacing. As you can see, the spherical layers, everything can be measured, not only at a one spot, but at various depth without breaking, without in a non-destructive way. So this is some capabilities that no other instrument can do. There's nothing AFM, SEM, TEM, or X-ray, or whatever you can think of, nothing can do this except this technique. And also, we can also then, as you know, the artist rendering over here, do we really see that? With this technique, we can go deeper and see the 3D distribution of the polymers, and as well as the quantum dots are in the center of those cylindrical formations. So what X-ray saw, what the rendering was done is actually visualized by the non-destructive terahertz 3D imaging. This is also not possible by any other technique. So this is some unique feature I have to share with you here. So visualization and quantitation of lattice dilation was the another example that I was going to show, but I think I already have taken 26 minutes. In conclusion, RB diffraction limit has been overcome by the bigger wavelength terahertz radiation. Cameraless imaging system achieved sub-nanometer and lattice resolution image with Hertz radiation in the X, Y, and Z direction. Combination of a smart nanoscaling spectrometer and algorithm replaces a CCD for sub-nanometer resolution, angstrom level resolution. It has a lot of applications. Here are some other summary of images. On the left, alumina, which is an amorphous material, but an amorphous material is not actually, doesn't mean that it don't have any lattice structure. It still has lattice structure, but those nano grains are all different lattice structure. That's what makes it amorphous. If you're on the right, as you can see, this is the lattice image of graphene. So the graphene forms a lot more regular structure than alumina. The gold nanoparticles are shown here. 2 gold nanoparticles side by side, their resolution are pretty good. And the layer by layer ability, as I demonstrated a minute ago, this is 3 layers are shown here only. This is the epitaxial semiconductor and gallium nitride lattice damage that is visible by this 3D image. Now with that, do I have time to go into spectroscopy? Probably I can take a few more minutes. So terahertz spectroscopy is the most sensitive form of spectroscopy. As you can see, even in a water molecule, there are so many resonance states, but ordinary FTIR and that kind of spectroscopy cannot see them because of the lack of sensitivity. The terahertz is the highest sensitive because it responds to the molecule as a whole, where there are many resonances possible, as opposed to just bond vibration detected by FTIR. So we build the spectrometer with the same terahertz source as a terahertz time domain spectrometer. So this time domain signal goes through Fourier transform to generate the frequency domain spectrum, and some calibration has been done with water system, with collaboration with other groups, and with polyethylene. And then we generate and reproduce all the peaks that others have seen, but we also generate more that others have not seen. Therefore, this technique gives us a way to do new science and new technology. For example, here is a test sample that we received from the Department of Homeland Security. It's a explosive. It's not an explosive. It's a similar molecular architecture, but the disk that they sent to us had one side is smooth and the other side is rough. The idea is that even if we do measurement in the rough side or smooth side, we should get the same spectrum to identify for the material for what it is, and indeed we get the same spectrum. Then here is the example of nanoparticle ligand system. We have nanodiamond, and the blue spectrum is the nanodiamond, and the red is nanodiamond ligandized with amine group. So there is not much weight difference between these two. They're very closely based in weight. And yet terahertz is so sensitive that it can see the small difference. Another example is the wafer on which self-assembled monolayers have been attached with two different same molecule. On the left, one has the 18 carbon chain, and on the right, this one has only 8 carbon. So if we take the spectrum with terahertz T-ray spectrometer, we can see those differences which cannot be seen by FTIR. And also the other thing, layer by layer spectra, not only image, but also we can go deeper in layers and take spectrum. This is a silicon germanium system, which we have inspected, and these results have been published. So the summary plot is here that we can see the surface, and below the surface of silicon, of germanium and silicon germanium. So spectra, germanium spectra on and under the surface can also be inspected. As you can see, there is some difference on the surface, thickness equal to 0, the green curve, and the other curve is at 25 nanometer deeper. So this is a tool that gives us a very versatile usability in semiconductors, in nanomaterials, and so on and so forth. With that, I will stop here. If you have any question, please feel free to ask.
Thank you very much, Dr. Anis Rahman, for such nice presentation. And if anyone